Okay, now let's turn our attention to box plots, a really common type of visualization for data. Box plots are useful for demonstrating kind of the range of values across certain categories of data. So in this case, let's use a data set called BA cups, Bronze Age cups, from the ArcData package as we did before. This data set contains a bunch of measurements on ceramic cups from Italy in two different time periods, the early and the late Bronze Age. So if we use the Boxplot function and plot the rim diameters, RD, of this BA cups data frame, we can see that the values pretty much range from around 6 centimeters in diameter all the way up towards 30. Now this is just all of the rows in that data frame, regardless of what time period they're from. And what a box plot does to visualize these data is it divides up the values into quartiles. A quartile refers to 4 different divisions of the data, 2 on each side of the median. So the first quartile here runs from around 6 to 10 centimeters. The second quartile runs from 10 to maybe 12 centimeters. And then you have the median, which is this dark black line here, right around 12 centimeters. Then you have the third quartile, which runs from around 12 to maybe 18 or 19 centimeters. And then finally the fourth quartile, this big long whisker up here, running from 19 or so all the way up to nearly 30 centimeters. And so that's what the boxplot function is doing. It's taking the data that you feed it, this set of values here in this column of BA cups, and it's dividing it up into quartiles and showing you the median and the range of those different quartiles. Now, we can also make this box plot show us these different values, but divided up by time period. So if we inspect our data, pull up BA cups, we can see that we've got the RD column, rim diameter, and then ND, which I believe is neck diameter, various other dimensions, and finally we have a phase column. If we inspect that phase column, we can see that, again, it's a factor vector with many different values, and there's 2 levels here. We see Proto-Apennine and Sub-Apennine. These are 2 different time periods in the Bronze Age. And what we can do is take that column of factors and use this kind of formula syntax here in the boxplot function to say, all right, plot the RD column of BA cups as a function of the phase column of BA cups. And when we run this, what we're going to get is 2 different box plots on the same plot. The first of these is showing the Proto-Apennine rim diameters, and the second is showing the Sub-Apennine rim diameters. This box plot doesn't actually tell us kind of what these values are. If you wanted to inspect what the median and kind of the minimum and the first quartile and everything are for each of these box plots, you can use the summary function in R. So if we type summary BA cups $, rim diameter, for example, that would give us the overall summary for all of the different values for both time periods. If we wanted to be more specific, we could say, well, we would need to use indexing to kind of crack open this BA cups data frame. So if we index that and say BA cups, and we open brackets, and then we say BA cups phase equals Proto-Apennine, and make sure I spell it correctly, and then put a comma there. What this code here is doing is saying, all right, take the BA cups data frame and index within it. That's what the brackets are for. I want you to index all of the rows, because we're to the left of that comma there, all rows for which phase is equal to Proto-Apennine, and then give me all of those rows, but all of the columns. If I run this, it would just create kind of a subset of our data frame. But what I'm really interested in is just that RD column. So if you were to take this indexing and add a $RD to the end, it actually becomes equivalent to saying BA cups $RD, but instead of all of BA cups, it's just the subset of BA cups that you're indexing. So if I run this, it just spits out those 20 different values of rim diameters from the Proto-Apennine period, which is really cool. So you could assign this to an object and then run the summary function, or we can simply just run summary on it as is. And we can see here that the median value for the Proto-Apennine rim diameters is 10.75, which looks about right based on this box plot. And obviously it is right. We can see the minimum value is 6.6, the maximum value is 19, and we can see the breakdown of the first quartile here and the third quartile here. If we do the same thing, we can copy that code, but instead of Proto-Apennine, we put Sub-Apennine. We can now see the median value for the Sub-Apennine period is actually more than 15 centimeters in diameter, ranging from 8.7 all the way up to 29.5. So this fits with kind of what we're seeing in the box plot, of course, and now we have actual numbers from these summary functions that we can use to understand what exactly it is that we're plotting, what these quartiles of our data are. Now, this box plot function that we've got here, let's dress it up and make it look a little bit nicer. So instead of just this simple version, there's a lot of different things we can do as usual. We can change the Y label, right? BA cups $RD. Anytime you've got the $, that kind of syntax showing up in your axis labels, it's probably a good idea to change that. We can say rim diameter in centimeters. We can change the X label to be phase. If we run that, we've now got some cleaned up X and Y labels on our box plot. We can also change the color of the box plot. Let's use the hex code trick, and let's make it red, FF0000, which I know off the top of my head is the hex code for red, and let's make it 50% transparent. So that just adds a little splash of color to it. And what we can also do, there's kind of another trick that was in vogue in archaeology for a while, and I haven't seen it much lately. But if we say notch equals true, or notch equals capital T, and put that argument inside the box plot function, this is what we get. It creates notched box plots. And the box plot function is doing something behind the scenes to figure this out, but in essence, what these notches are can kind of approximate confidence intervals in a sense. If the notches overlap with each other, it's probably not a significant difference between the two sets of values, a statistically significant difference. If the notches don't overlap, if they're actually separate from each other, that's probably a significant difference. Whereas if they're overlapping, there's probably not going to be any significant difference between them. Now, as I said, these notched box plots, I haven't seen these in a while, but you will encounter them in archaeology from time to time. It's good to understand what they can do, and if you like them, you can use them as well. But I would say that these are not a substitute for actually running a hypothesis test or a model on your data. Now, I do want to make a note about box plots here. Box plots, I'm going to change this back to notch equals false. Box plots actually have been criticized a lot because they obscure a lot of the details of your data, right? It breaks up into quartiles, which is nice, but you don't actually know from looking at this box plot how many different data points there are, right? That box plot for the Proto-Apennine period could be based on 10 points. It could be based on 1,000, and we don't know from that box plot. We don't know the distribution of those points across all these different values of rim diameter. And so if you're going to use a box plot, and there are some that argue that you shouldn't, but if you do use them, because they are still common, what I would recommend doing is using the points function to supplement the box plot and actually add the data points themselves. So if I were to say points BA cups RD as a function of BA cups phase, let's say PCH the point type. Let's make it 16 because that's my personal favorite. And let's set the color equal to a sort of transparent gray. 50% transparent black, I should say. So here we've just put the actual data, the actual observations, the actual measurements of rim diameter on top of our box plot. So now we can kind of see a little bit better how these data actually fall out across all of the range of rim diameter. We still have the quartiles from the box plot, but now we actually have a bit more information and we can see the data points themselves. This kind of looks a little bit messy, though. It looks okay because I made the points transparent. If they weren't transparent, it would just be a bunch of black dots on this box plot, and you get kind of a bunch on top of each other. By making it transparent, it's a little bit easier to see that there is a bit of kind of spread to them, and they're not all just on top of each other. But there's another thing that we can do to make this look a little bit nicer called jittering. Jitter. Jittering refers to kind of adding a little bit of random noise, a little bit of random variation around your data in order to make it a little bit more aesthetically pleasing in most cases, and in some cases it can even be used to obscure. For example, if you're an archaeologist and you're reporting real site coordinates, oftentimes you don't want to report site coordinates because somebody could come along and loot that site. And so you could jitter your site coordinates and add a little bit of random noise to them so that somebody could still replicate your analysis, but they wouldn't be able to actually locate that site in order to engage in criminal activity, for example. But so in our case, jittering is useful because we can simply jitter the points to spread them out a little bit and make this plot look a little bit nicer. Now, we don't want to jitter the actual rim diameter values because that would then change the actual data that we're dealing with. But if we jitter the phase a little bit, that allows us to spread out these data points across the horizontal, across the x-axis. In order to do that, we need to first say as.numeric and wrap the phase vector in this as numeric argument. And what this does is it takes the proto-Apennine and sub-Apennine levels of that factor and it translates them into ones and twos. It assigns what's called a dummy variable to each of these categories. If we then, because if we tried to just jitter these, you can't add random noise to the word proto-Apennine. That doesn't make any sense. You need to take proto-Apennine and sub-Apennine, turn them into dummy variables, into dummy numeric variables, because you can only add random noise to an actual number. So that's why I use this as.numeric function to change sub-Apennine and proto-Apennine into a bunch of twos and ones. Now we can jitter that. So if I use the jitter function here in R, and I wrap all of that around. Actually, I wrapped too much. I put that end parentheses at the end. I want to put it here. And so if I run that box plot again, and now I run the points, you can see that our data points that we've plotted are out now actually really nicely spread out. So we can see a lot more clearly how these data are falling out. These data are still in two categories. It's just kind of simulating this idea that it's ranging across more than just values of 1 and 2. But we can still understand it as kind of these are two categories of data. It's just a little plotting trick to make things look nicer. You can control, if you inspect the help file for the jitter function, you'll see that you can control the width of the jitter by how much you want to jitter it. So if I run this again, I've made it a little bit tighter now around values of 1 and 2, just to keep it from getting way spread out, because you don't want these points to start running into each other here in the middle. So this jittering is just a nice little trick that you can do when you're adding the actual points to a box plot, or when you're dealing with categorical data in a bunch of other ways. Jittering is definitely something to include in your repertoire of kind of R skills. And as I said, it's really useful when you're dealing with box plots, because a box plot by itself really actually obscures quite a good bit of data. But if you can add the points on top of it, you get some of that resolution back, and you're better able to see exactly what your data look like, and be able to better understand what exactly it is you're dealing with.